Hey, welcome back to Fat Mama Physics. In this video, we're going to do example 3, no, I'm just kidding. Example 3, which is a fission reaction. Whew, lots of stuff to calculate. And calculate the amount of released energy. Nuclei data for the nuclear fission reaction illustrated in figure 3. Try calculating the amount of released energy through finding A, the mass defect, and through binding energy per nucleon. So we did that in the last question, but I guess we will do it again for extra practice. And this is going to be extra annoying because there's going to be even more things here that we have to calculate. But alas, let's just get to it. The other thing that is annoying here is the fact that we're given the atomic mass and we're not given the nuclear mass. So we have to go in and just subtract the electrons off of each of these guys before we go ahead. That's annoying. Okay, so I'm going to add another column, another row, and that's going to be our nuclear mass and per unit of U. Okay, so the nuclear mass is, of course, going to be the same for the a neutron, but for the uranium, the uranium atom, assuming it's a neutral atom, it's going to have 92 electrons. So we're going to minus the mass of 92 electrons here. The mass of an electron in terms of unified atomic mass units is 0.30549. So I'm going to do that to give me the nuclear mass of uranium. Actually, I'm going to do one example down here so you know what I'm doing. So I'm taking 235.043930 atomic mass units. That is for the atomic mass of this uranium-235. I'm going to subtract the electron mass, which is 92, assuming a neutral atom, 549 atomic mass units to get rid of the electron mass from this number. And for this one, I get 234.993422. Okay, a little bit smaller, but not that much smaller. So I'm going to do exactly the same process, but for, I guess this is barium, so I'm going to have to subtract 56 electron mass units. And for krypton, I think it's krypton, this is going to be 36 electron mass units. So after doing that, I'm going to get the following. Okay, and these are the numbers that I get. Okay, so this is, that's just for completion there. Okay, so I'm going to be working with nuclear mass and not with binding energy per nucleon. But the first part of the question, in which I do look at binding energy per nucleon, I'm probably not going to even need the nuclear mass units. So let's go ahead and do the binding energy method first. I'm going to do B first. So that's going to be, this is looks like a spontaneous reaction, meaning that I'm going to have more binding energy in my products than I'm going to have in my reactants, since I'm going to have more stable nuclei at the end. So more binding energy, meaning I'm going to do barium, krypton, and there's no binding energy per nucleon for the three neutrons. So I'm just going to look at these two numbers first. So the 8 to this one and the 8.6, these two numbers multiplied by the nucleon number of barium, krypton, respectively, and subtracting that for the uranium. And it looks like I don't even, oh, okay, so this is, so almost confused me here, but this one here is just a medium, it's just an intermediate step. We don't have to worry about this. Essentially, you have this side versus that side, okay? So let's go ahead. I'm going to take the 8.61 multiplied by the number of nucleons in krypton, which is 89, 144 in barium, and 235 in uranium-335. Okay, so those are the big three nuclei that we have to take into consideration. I get a whopping 173.27 ... and rounding up to, well, I guess 4 sig figs, 1 or 3 is probably sufficient. 173 mega electron volts. Okay, so that's using the binding energy method. The next up, I'm going to use the nucleon, the mass defect method. With the mass defect method, I'm going to have to use my nuclear masses, the ones that I've calculated earlier. So again, we have to be very careful because we're not talking about binding energy. We have to use all the masses that are on either side of the equation, including these 3 neutrons and this 1 neutron here. So you're thinking respectively, I have a net 2 neutrons I have to consider on my product side. Yes, let's do that. So here I just wrote a note here to ourselves. So then we will be doing, we will again compare the masses. We know that since we're talking about a spontaneous reaction, we will expect there to be more mass in our reactants versus that of our products, because that's where our binding energy is going to come from. And the energy that's released is going to come from. It's going to come from that mass from our reactants. So that's going to be the uranium-235 that we started off with. And this guy is right here. So starting with 234.9, this is the atomic, nuclear mass of our reactants. And now I'm going to subtract everything else, including the 2 neutrons in our products, because we have a net of 2 neutrons here. So I just used the atomic mass for the neutron because, assuming it has no electrons, I just took 2 of those from there. So if I subtract everything, I get 0.190167, and multiplying by the energy per atomic mass unit, which is 931.5 mega electron volt, C to the power -2. This is going to give us... Okay, so I noticed I had a bit of a mistake in some of my initial calculations, and involving the electrons, the number of electrons, and finding the nuclear mass here. So this number here for barium, we should have one for 3.892197. And even a little bit of a small change is going to result in a large amount of energy, so a difference. So that we have to be very careful. And then same thing here with krypton, 88.897868. Okay, so if we go back and use these correct numbers, then we should be able to get exactly 173 mega electron volts. So let's, since I've adjusted the masses here, I am now going to recalculate our total. This is 0.186027, and then multiplied by 931.5, I get 173.28, which is pretty close to what we had before. So there we go. Okay, and one thing that I know we calculated the nuclear mass instead of just using the atomic mass, but there's a unique case in which if your electrons in your reactants are exactly the same number of electrons in your products, then when you subtract them, the terms will go away, which means you'll have no net gain or loss of electrons. So in this case, if we had just used the atomic mass instead of calculating the nuclear mass, we actually would have been okay, because 36 plus 56 electrons gives us exactly 92 electrons in our reactants. So the electrons, there were no loss or gain of electrons in our case, meaning that it did not matter. But of course, when we're talking about nuclear reactions, we technically should be using the nuclear masses, just in case things like electrons don't balance out. Okay? Woof! Alright, so thank you for bearing with me, and I know that these calculations can be very tedious, but it's but hopefully along the way you'll be able to learn a few shortcuts and tricks up your sleeve to make your lives a little bit easier. So I thank you for watching. I wish you the best of luck. Make sure to get to the practice, and Fat Mama Physics signing out.